boundaries between regions essentially correspond to contours, for example, or curves and lines. And one of the things I mentioned without elaborating is how to find an edge between two regions in terms of the rapidity of change with respect to position as you migrate from one region to another. If you go along an edge, you will hardly see any change, but if you go across an edge, you will see a very abrupt change, and that abruptness of the change is essentially what we are trying to catch in terms of these differential operators that I had shown you earlier, these differential operators. Now, there are various formulations this with better performance depending upon what kind of data you have, all kinds of things. But fundamentally, it is about detecting the abruptness of change, setting a threshold on how abrupt at least it should be, because change is likely to be found in many places. But we only want a real abrupt change to be reported as an edge, as a point of takeoff from one region to another region. So, as I said, we take the second derivative and take the peak of the second derivative. That gives us the point where the abrupt of the change or the gradient maximum. This, and then we move from the edge, do it again, and thus create the set of points that constitute the boundary between two regions. This itself is a segment, but curve between the two could be the object of interest for us in many situations. For example, when you are detecting a human face and things like that. And if you remember the first few slides, we had talked about finding contours as tasks come under what we call segmentation. So, this is what we have over here. And then after this, there are basically lots of descriptions about various operators which give you edges, and the canny edge detector is one of those that is very well known. I will not go into an elaboration of how it works very well, but basically it tends to do several things to make up for irregularities in the data. For example, when you are tracing an edge, it gets broken somewhere because the gradient is not enough to be reported above the threshold. It fills up the gaps, and there are several other things it does. It has several parameters which you can set to make it more sensitive and pick up a lot of edges, or less sensitive and pick up a smaller number of edges. So, both these things are possible with the canny edge detector. All these kinds of variations are possible with the canny detector. The canny detector is used pretty often, and it is quite good when you want to segment images for human use, and that is why I wanted to mention it to you, because people will just run the canny operator on MATLAB or something without knowing what its strengths are. If you look at these images, you will see that depending on the thresholds you set, for the first image you may get the second one in the top row as the output, or the third one depending upon how you set the parameters. So, there is still the need for human to basically certify what level of edge detection is being sought the user. It is not completely automatic, it does not know your mind. Now, kidney. So, this is, you can see this supposed to be a kidney, I do not know. Yeah, I mean, it looks like, I mean, it could be anything for God's sake, but anyway, you can see there are a lot of edges detected. This is precisely what happens when you set the thresholds too high, or rather too low. I am sorry. When the thresholds are too low, even minor changes are reported as edges, and you get a lot of edges. Now, any attempt at automation is always accompanied by this kind of leeway that exists. depending upon how you adjust your thresholds, these are often called, what is called, meta parameters or something like that. Yes, and they need to be set by um, some human semi-automatic intervention. This is that image which you have seen many times in the earlier slides, whose edges have been detected pretty nicely by this scanning edge detector. Now, you can look for closed regions within this and assign them to various segments. This will help you segment the regions in a way that was better than just the RG grow algorithm that we looked at that time. Finally, having crossed this, we want to look at the Hough transform, which I mentioned yesterday. Maybe a little use of the board would bring out the of the Hough transform without taking too much time. Okay. You see, what you get in an image would be a lot of dots. You might get some slight continuities like. Now, if I ask you how many straight lines are in the picture, you will probably say there is one which is very badly detected, because there are places like here and here where pixels are missing, but it ought to be a solid straight line. Now, that is the feeling you get by looking at it, because our neural network automatically tends to line up these pixels and say, look, they all are collinear, so they should be contributing a line. And how does the program handle this? How does it get the feeling that all these are in a line? Very simple. Now, let me take this pixel and say this pixel. I can pass a line through them. They could be part of some not properly defined straight line. I could take this pixel and this pixel, and there could be a line like this, but then they are the only two which are lying in that line. Now, if you look at this and say this, there could be a line like this. If you take this and this, even there could be a line like this. All these are definitely possibilities, but as you see, if you extend, say, this line, there are hardly any other points on that line. If you extend this line, hardly any other points on that line. If you extend this line, there are hardly any other points on that line. This line, hardly any other points. So, this is looking at it, the Hough transform looks at it from a political point of view. It does not say whether 2 points constitute a line, every 2 points constitute a line. So, it is like saying every 2 people in this room can form their own political party, but is it a significant political party? That depends upon how many people join you. That is exactly what is happening over here. You take all these points, there are so many here, 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 here. You take these two, you get a line like this. You take these two, you get the same line. You take these two, you get the same line. So, there are several points, pairs of which all agree upon the same line, and that is what matters. So, if you take this line, there is some M1 C1 with this. For this line, there is some M2 C2 associated with this, may be some M3 C3, this may be some M4 C4. So, for each of these, you go to an MC plane C, and then you plot for every pair of points which give you a line, you will get a dot in this one saying, yeah, I got one, I got one, I got one. Now, there are, if there are 100 points in this edge detection, there will be 100 C2 lines you will get. So, that is a lot of dots, but at some point corresponding to M4 C4, which may be around lot of dots, because there are too many point pairs asserting that M4C4 is a popular choice, and that is where you will point and say, yeah, I mean there are some slight variations, it will not be so wide, it will be say here all the points will be within this. We say that yes, with some minor variations, this is the set of points that constitutes a physical line, a physical straight line, and that is what you will report, saying that yes, I found a line. This has a lot of amazing utility, because it helps you to make an algorithm which almost looks at it the way a human being would look at a collection of dots and connects dots which lie in a straight line. There is no other simple way of doing it, and this is brilliant, except that pretty expensive to do. You imagine the number of MCs you have to calculate. As I said, if you have 100 points, you have got 100 C2 points, 100 C2 lines to make, and each of those MCs should be plotted on this, and then the most popular one corresponding to the peak of the distribution should be picked up. This, yes, is the cost to be paid, but with this you are really able to make sense out of a jungle of points, and that is what is so beautiful about this. And this idea of looking at a jungle of points and seeing a line in them, to see a circle in them, to see an ellipse in them, to see other more complex geometric objects, because is to express it in closed form, whatever object you want to look for. Like you want to look for a circle, as I said yesterday, express it in closed form. Formula for the circle, x naught x minus x naught whole squared plus y minus y equals, right. Now you have got x naught, y naught, r. X naught, y naught are the coordinates of the center of the circle, and r is the radius. So what you do, you make a three-dimensional histogram, plot a distribution of various circles you can fit into the dots, and the most popular circles will pop out automatically. So that is the story of the form, which in classical signal processing is probably one of the smartest things around. Okay. Now, having made these comments, I think we should really move on to today's topic, which is going to come now. If in this first lecture that I just concluded, our concern is with finding out what is there in the picture, like I was saying, oh, where that, yeah, this is my favorite toy. Finding out this object exists in the picture was the first exercise. Now, this lecture is about finding out where it is, not whether it is there, but where it is, because that in a robotics context determines what the next move will be, where the robot will move forward, towards the right, whatever. Now, there are tasks where you just have to find the location of an object in an image to track it as it moves around. There are places where you have three-dimensional information about the scene, and you actually have to find out where this object is in three-dimensional space. That is understandably more complicated, but eminently doable. So, this is the business of image registration. So, always, unlike segmentation, where you just take one image and you try to make all kinds of sense out of it, generally you do not need a sequence of images, you do not need a video to do image segmentation. You probably, in fact, if you have a video, you will have to do the segmentation separately in each of the frames of the video. Here, it is all about how things change or evolve as new frames of the video come to you. So, this is all about moving things. This is not about a static picture. Okay. So, here we are. What is the task of image registration? You have picture 1 and picture 2, maybe the board is, I guess some of us are addicted to the board. We are not, we can't think entirely in terms of slides. The slide throws all the information at one go on you, and it kind of takes away the surprise element that we would like to keep for ourselves. Let us say you have this is one frame of picture and another frame of a picture. Fine. Yeah. Put some object, let us say a little cross in this place in this picture, and let me put this cross over here in this picture. So, in my video camera, this object occurred here in the nth frame and it occurred here in the n plus 1th frame. Now, my job is to understand why it did that. Either the object moved or the camera moved. You know, I can make you all move by just turning my head. So, you will all appear to move in the opposite direction. So, in order to do that, in order to evaluate how much the camera has moved in this case, let us say, or the object has moved, one has to correlate the position of the object in this frame with the position of the object in this frame. Basically, I want to find out whether a certain horizontal movement of this frame coupled with a vertical movement of this frame can make me match up this point with this point. And you can see that it is true. I just have to draw this frame on top of this frame like this. Now, if you look at this cross as belonging to this frame, you will see it is in the right place. If you look at this cross as belonging to this frame, then it is in the right place. So, what I want to evaluate is this difference in position, this vector. I want to evaluate what is the amount of shift. However, that is possibly the simplest formulation of the problem. Things can be more complicated if the object is just not moving like this within the plane, but it moves in depth as well in a three-dimensional scene. Then things take a more complex appearance. But this is the way to start talking about it. Now, when you have taken the first frame of this scene and the second frame, what are the things that have changed? The things that have changed are the position. It was x naught y naught in the first frame and it become x1 y1 later. Now, I find transformation f that takes x naught y naught to x1 y1. That you see changes the argument of the function. I x y is the original frame, I1 x y was the original frame. Now, I want to write the second image in terms of the first image. That requires me to shift the points in the first image using the function f, and also with pure practical considerations in mind, probably change the value of the point, the brightness of that point. It is the same green colored point maybe, but maybe it becomes a little brighter, little natural illumination, ambient illumination, in sunlight, move to the shade or whatever. So, I will have to change both the domain using f and the range using g. If I do both this, then I should be able to write that the left side I2 x y is equal to the right side. So, what is my job? My job is to find g and f which satisfy this equation. G and f that will match up I1 x y to I2 x y. That is the job. That is fundamentally what we want to do. So, as is clearly mentioned there, f is a two-dimensional position transformation, a spatial transformation, and G is just a one dimensional intensity transformation. It can be three dimensional as well if we are dealing with color images, and the greenish things can start looking slightly different. You might have seen these rupee notes, both the new ones and the old ones, though you can't see the old ones now. If you tilt them in different directions, some parts on the note change color. So, objects can change color depending on the and depending on the direction in which light is falling on them. Not very common, but yes, it happens. That is why G can be a three dimensional function, a function of three variables. Okay. Assume the correspondences are known. That is, we know that the object was there earlier and now it has moved there. We know this. That is a separate job, and we will talk about that as well. G and F is the business at hand. Okay, right. So, there is a hierarchy of these transformations, spatial transformations, starting from the rigid to the affine and the projective and the perspective and the global polynomial and the spline. Essentially, if I tell you what each of these is, you will be able to appreciate how the problem of registration can progress from the extremely simple to the reasonably complicated. For that, image and create a second image from that by changing something in it. Maybe sliding it around, which is just a translation like I have shown on the board. Maybe stretching it, maybe shrinking it, maybe twisting it, maybe doing all kinds of things. And to just give you an example of what each of these things mean, I would probably like to go to another set of slides which I had made for my course. Just give me a moment. Geometrical operations. Okay. Here is, a picture is worth 1,000 words, and I am going to show you not thousands of pictures, but a dozen of them. So, that is like 1 dozen 1,000 words I am going to give you now. Okay. So, these are essentially the things that I have told you already about different kinds of transformations. Let us go to the pictures. Yes, here we are. Horizontal, vertical and diagonal shifts. Right? You can see horizontal shift, vertical shift, you can see the diagonal shift is also there. These are of the kind that I have shown you in the board over there, and the diagonal one is the last one here, where that was an example of a diagonal shift of some amount. So, this is one of transformation, this is a rigid transformation. Now, the next case is a linear geometric operator, which can also involve rotation. Look at the second picture below. See, the first one is just, as I said, translating it around, only translation, nothing else, moved by a certain amount horizontally and vertically, but remaining unrotated. In the second one, it has got rotated. So, in fact, you can do both, and that is when you will have a matrix like this with no zeros here. This one is only rotation without translation, that is translation without rotation. The theta by which you rotate will be implemented by those sine, cos, that part of the matrix. So, if you do this, you are going to essentially reposition each pixel of the image to the new positions that will give you the new image over here. The next thing which gets more complicated is when you want to scale in the x direction. I have scaled that image horizontally by factor of 3, and you can see what it looks like after you have done that. Fine. The next, as you can see, is scale in the y direction, and you can see this where what the matrix looks like when you do each of these things. All these are still a small part of the more complex transformations you can make, but this is y scaling, that is x scaling. Next, shear. Well, you know what is shear. So, here is what we are doing, this is shear, shearing the image. And where do the matrix entries come in? You can see the amount of shear is 0.3 and it has come there. And the other one is y shear, and y shear will, by this factor, will give you this kind of result. These are all examples of registration problems. This is no longer a rigid transformation, for example. Why is it no longer rigid? Because if you do it to a real object, it is no longer going to remain in a fit condition. But these things can happen merely because of the angle from which a new photo is taken, a new picture, a second picture is taken. So, here you have got shear in both x and y simultaneously on the top, and the last one is not just shear. You see, shear is always a symmetric thing. It will give you rhombuses or it will give you parallelograms. It will not give you this last object over here where you are doing a perspective transformation, right? Projective transformation. This is what you get when you do that. I guess that is the last of my slides, where here we have done all kinds of things at the same time. Rotating, projecting, shearing, I do not know what is there. I mean, you can look at the thing, you can see all kinds of things have come in, and this is just a visual way of showing you the kind of transformations you can do to an object. And my registration problem would essentially mean that if I was given the original picture of Lena and this last one, from these two pictures I should be able to get every entry in the matrix, should be able to get all these numbers. If I do that, then I will say that I have registered the second image to the first one. Suppose I want to register the first image to the second one, what would that be? It would be the inverse of this matrix. It is like saying, why do the whole eat bread for breakfast? Is people reasons. One, it is popular. People have been doing, and there are actually a few technical reasons. Maybe I will spend a minute just to tell you about them. The Lena picture is very, very interesting because, to evaluate the performance of an algorithm, you should have all kinds of features on the image. You should have textures. Lena's hat has got a nice woven texture, you can see. So, we can see how our algorithm worked on the texture. If you look at Lena's face or Lena's shoulder, you can see a smooth, gradually varying change of shading. You can see whether some algorithms are giving rise to artifacts if that smoothness of the shoulder or the face get disturbed. You can see edges like the edge of the hat. It is not a straight line, but it is an edge. There are also straight line edges in the image which you can use. And then there is Lena's hair, and Lena's hair is an example of long edges of of high detail, because each hair can be seen in a good picture. So, you have got high frequency content, you have got low frequency content, you have got texture, you have got slowly varying smooth surfaces, everything is there in this. Interestingly, apparently this is just the face of the person, and the rest of it was not considered to be fit for image processing. And Lena was apparently interviewed on her 80th birthday or something. She is, I do not know if she is still around today, but probably the most seen picture. Yeah. So there are technical reasons why this picture is so popular. The reasons are the various kinds of phenomena that are observed here. You also see defocused regions in the back. You see all kinds of things in this picture, and that is why it is a good test. There are several other tests like this. Now, what happens in the technical community is, if you create your own images and show your algorithm's performance on them, they will say, well, it looks okay, but I would still be more convinced if you did, because it is a standard now. It is a standard data. So, it is like, civil engineers will have something like, if does it have the same standards of the bolts as that particular specification given by ISO or something. I can always say, why should I follow that? I invent my own nuts and bolts. No, you can't do that. You have to follow the standards. So, this has been elevated to the level of a standard, and it therefore is like a benchmark test. Ah. Uh-huh. Ah. Yes. The two image arrays you are saying, yeah, they are not really matrices. Even I used mathematics professor told me, how can you call them a matrix? A matrix is a linear transformation. Can you take a vector and multiply it by lena and get something else? No, lena is not to be understood as, I mean, an image is not a matrix. Yeah, yeah. Okay, the data. Yeah, yes. All you have to do is to slide it one row. There is only a translation. This is exactly what I am going back to now, the registration problem. That is exactly how we do registration. Now, let me close this and let me go over here. The thing is still open, I guess. Yeah, there we are. So, this is much of what is said here, what is being said here is has been picked up by this. So, you can see here rotation, translation, scale and shear. We have talked about all these already. Fine. Perspective transformations are basically what you call planar homographies, and for each of these, as the transformation gets more complicated, there are more numbers to be found out. If you had a look at all those matrices, the earlier transformation had only a few non-zero numbers in them. Of course, there was 1, 1, 1 along the diagonal. Even if you take a transformation that does nothing, what would be the geometric representation of that matrix representation? It would be the identity matrix. You are going to have 1, 1, 1 along the diagonal anyway, which just says keep each pixel right exactly where it is, do not do anything with it. So, it is the deviation from the diagonal, or rather the identity matrix, that makes for a non-trivial transformation, and therefore, it is those numbers that we need to find. And as we go to more complex like the transformations like the perspective transformation, there are more numbers to be found out. So, if you have image 1 and image 2, you have to first find out corresponding pairs of points. For translate, see what its exposition is here and what the exposition is in the second image. Similarly, do the y positions, you have the translation. If it is rotation, so you need only one point. If you want to do a transformation like this, then you gradually start requiring more and more points. As we go to more and more complex operations, this is going to get even more complicated. You will probably need 8 points, 5 points, 7 points and so on. And there are always computational errors, and there are also errors in finding the point pairs themselves, and all these will make this business a little more interesting and complicated. Okay. Perspective transformation, you have to, those are the world coordinates, and you can see the transformations that relate these points. Okay. Projective transformations, something slightly different. You can see that xi and yi are given by this kind of ratio of polynomials. So, if you want to find, basically, if I find the projective transformation, what does it mean to find it? I have to find the denominators a in both sides and the numerators a. There are totally a21, a22, a23, a31, a32, a33 and up a11. So, there are 9 numbers to be found. If I wanted to find the 9 numbers, then I have to find points, because each point gives me an x and y. and so you have 5 points equations. That is the minimum I need. Oh, sorry, not yeah, 9, right, 9. So, as the transformation gets more complicated, you need more points of correspondence. Okay. These now are really complex transformations. You can see how you need not only do the simple kind of things that I showed in my previous thing. Suppose you take a bat face, it's not going to be a simple or fatter, and even when you want to look thin and tall, find a suitable mirror. At least others may not think you are thin and tall, but you will feeling so. So, a general mirror, a poor quality mirror, if you have, I am sure you would have seen some of those, would give you that rectangular grid transformed into something that you see in the front, in the foreground. All kinds of local variations in the positions of objects. The positional variation in the left side need not be the same on the right side, what is above as the what is below. You really have to handle this in a very interesting way. You have to probably cut up the image into small pieces and find separate matrices for each piece. Which is to say, you are going to treat each little piece as a linear transformation, as the most general perspective projective transformation kind of thing. But each part has to be kind of handled separately, separate matrix created for it, and then you kind of stitch all these things together to make them come into one mosaic like this. That is the most general kind of registration problem you can think of. But this, I mean, this linked to all the previous things we did, because the previous things constitute the building blocks for this kind of a thing. Now, of course, the question will start as to how big can I make these chunks? Well, it depends upon how distorted it is. If the distortions are extremely gradual and smooth, then you can make big piecewise planar pieces and find a smaller number of matrices. Now, for each of those matrices from that respective local region, you have to find pairs of correspondence, I mean correspondence pairs in sufficient numbers. For another local region, you have to find them all over again, because it is a different matrix altogether. You have as many matrices as there are pieces. You need to have as many pieces as make a sufficiently faithful representation of the registration here. That is to say that ideally it is probably not fittable into a piecewise planar structure, but if you really want to do it, you can do it. And also ideally you should have a large number of small planes, but if you do that, your cost of computation increases. So, you come to a compromise somewhere and say, I am okay with 1% error in the position of a pixel. If you say you are okay with 10% error in the position of a pixel, you will have fewer planes to approximate the transformation, fewer piecewise planar regions. If you want 1%, then you will have more. If you want 0.1%, you will have still more. So, it depends. I know as engineers, whether you are solving the problem for some space application or whether you are just doing it for somebody's drawing room television, you can accordingly find a global transformation. So, now how do we do this job? This is the story. Oh, okay, I got 12 minutes. I am slightly doing better than yesterday. So, correlation is one of the ways in which, as you were saying, you find where one image's position fits with the position of the same object in the image. A correlation, as we know, is just that expression that you can see over there. Oh, let me, if I do this, it will all go away, but anyway, let me try to do this. Ah, I did it. Okay. So, that is essentially an inner product, normalized inner product, and it will give you a peak, and that peak, the location of that peak will tell you what is the transformation required. Okay. So, the correlation theorem says that the Fourier transform of the correlation of two images is the product of the Fourier transform of one image and the complex conjugate of the Fourier transform of the other image. This is the kind of problem we give to solve in our undergraduate course on signals and systems. So, you can do Fourier transforms of both the images and then you can evaluate the correlation in the transform domain if you like. The correlation is not a number, the correlation is in a complete map, it's an image in its own right. And what you are therefore getting by this transform in the transform domain is the Fourier transform complete correlation image. Okay. Now, the transform based methods can do various things and I am not going, I do not have the time to get into this whole thing. You can use the phase of the Fourier transform, the Fourier transform is always complex. It has got the image and it has got a mass image or whatever magnitude image, both are there. So, you could use these various techniques to find it, and the Kepstrom is another very interesting approach, where you do not take the spectrum as it is, but you take the logarithm of the spectrum, because the magnitude spectrum is always non-negative. So, you can plot the magnitude spectrum and you can use that for doing it. This Kepstrom is a very interesting creature, and if I find time I will tell you how very interesting things you can do with it. So, point mapping is the other thing. You have to find control points and then you will basically use that to fit these connections between the two images. So, markers within the image can be found, for example, you have point features like features or regions of the same color in the two images can be compared to each other to find out the shift, to do the registration, or it individual pixel points which are called corners or 1 or 0D points give you far more accurate position for registration. So, you could write codes which detect points of high gradient and use them to connect one image to the other image, or you could manually assist it by finding the correspondences. This is about finding the correspondence pairs which I talked about. So, after the control points have been determined, the cross correlation, the convex hull edges and other common methods are used to register the set of control points. So, register means find the shift between them. Okay. Now, I should tell you something which you need to do. Even suppose you have a simple a purely automatic would hope reality of the way things go wrong when you ideally nothing should go wrong. So, there should be no at all, but nothing happens ideally. So, you could match a problem because if you do it manually, lesser chance code make wrong matches. So, what you are just now there is a set of points transformation like the last slide I showed some time ago. Then the amount of shift a particular feature should be same as the amount of shift of any other feature point. They can't be 2 points. Why do you need 1 dozen points? 1 point. That's point. You might even match the pair of points in this image and this image wrongly, or you might have minor inaccuracies in the positioning. Rounding off of a decimal because there is the register all the dozen points. Seems like an extremely horrendous because depending on the data and depending upon the critical thing, find the shift at all the, so again take a 12 points, take the mean of them. Totally wrong. And you know, since they are not agreeing with the majority that they have no business to be kept there, you just throw them out. They are called outliers, and you take the inliers and take the mean of the inliers. So there are serious time errors that are going to result in outliers, and then there are measurement errors, which are not correspondence errors, but which are errors of half a pixel, 1 pixel, and so on. So there you, the smart thing to do is to take the average of the discovered points. Okay, global polynomial transformation. So use a set of patched points to generate a single optimal transformation. So this is basically a polynomial you are fitting into the image. Okay. Now, in order to do this again, you have to be sure the same consensus principle that we just outlined. You will take, if you need say 5 points to fit the 5 dimensional for the 5 degree, 5 degree, then what you will do, you will 50 points or 100 points or even 5, and take 7 the pairs. Now, if you even have 50 points and you needed only 5, then there are how many ways of picking 5 out of 50? 50 C5 points sets you can get. Each of those will give you a different polynomial. Well, hopefully not different. Each of those will give you a polynomial. Again, the consensus principle says it's not universal, because there will be outliers. You can't say everybody has to agree on this. Everybody isn't going to agree. A few of them will not agree. They will have radically different opinions on it, on the values of the coefficients. Throw them out, because they represent correspondence errors and not approximation, not what we call measurement errors. All the others will more or less agree, will be close to agreeing, and those you will take the, and you will find a polynomial which is not exactly going to fit the points here to the points there, which is the best deal you can get under these circumstances. This is the global polynomial thing. Yeah. So, okay, then maybe I will just, yeah, this is a lot of, okay. Here are some examples where you want to align images. I think this pictures will give you a feel of it. The left side picture is taken with a normal camera kept at a certain place of that road and the background and all that. This is a normal visual band camera which is sensitive between 100 and 700 meters. It's a black and white picture. The right side picture, by the looks of it, is a thermal image taken with a thermal camera. Now, the second camera was not exactly kept in the same place as the first camera. That is why things look a little different. You know, when you take a picture, even if you move that camera a little bit, everything shifts. This second camera was not exactly probably placed where the first camera was kept. More importantly, it might have had a different lens specification, it might have a different sensor size, it might have a different number of pixels, all kinds of things. So, you have got this and you have got this finally, and you want to use the joint information of the thermal image on the right and the visual image on the left to give you a more informative, rich image. For that, you have to carry out an alignment. This is a rigid transformation, and in order to evaluate this rigid transformation, you have to find fine features which are highly localized, like points or lines and edges and things like that. And you can see that you can do it. This is a runway and you can see those zebra crossing like things close to you. You can take the left top corner of all the 4 or 8 zebra crossings there and here, and they will correspond to the same left top corners of the zebra crossings in this side. So, this is one set of points you got. Then you can take that. There are other things, that dashed line which you can see over there, not very good in the visual image, but you can see that in the thermal image. But that was rather example. Yeah, I am just coming back. Yeah, there we are, not bad, better than the Indian Railways. So, you can have same modality cameras, that is cameras of the same kind, cameras of different kinds. Maybe I really should stop here. Here are images with, let me quickly go through this and see if there is anything worth achieving in few minutes. Here is an example. Yeah, pictures are always good. What have I got here? Again, I have got 2 images probably taken with different modalities, maybe infrared on the right side and visible band on the left side, and they have been taken from different places. You can see their objects are in common. You just have to tweak one image so that it fits properly in the other image, and that has been done in the 2 lower images. You can see the tweaking has been done so that the objects match up properly. The left side, you have just cut them into little strips and interspersed them. You can see that the horizon is not matching, but after doing the appropriate transformations, the horizon is matching. One of them, the horizon, the sky is dark, the other, the sky is white, but that is okay. But horizon is horizon, and you can see that they have all matched up properly. However, you are not showing both at the same time, because I can't. So, obviously, this entire image is available, both the images have been aligned properly, and having done that, now it is the visible image which has been tweaked in this case. This right side image has been kept untouched, and you can see that we have achieved pretty good alignment. Okay, that is it.